Right. Welcome, focused learners. Let's jump straight in. If you're tired of just, memorizing a giant list of confusing geometry rules without actually getting them, you are in the exact right place. Today, we're decoding the absolute truths behind circle theorems for the Cambridge IGCSE Mathematics 0580 syllabus. We're going to take what looks like a chaotic jumble of lines and angles and turn it into a beautifully logical system. No more guessing, just pure understanding.
So here's our roadmap for today. We're keeping it incredibly straightforward with a define, prove, apply structure. We'll hit cyclic quadrilaterals, the alternate segment theorem, equal chords, and then we'll actually apply all of this to some real problems.
All right, kicking things off with our first major concept. Let's look at what happens when a shape is perfectly trapped inside a circle. First things first, what actually is a cyclic quadrilateral? Well, it isn't just any random four-sided shape. It's a specific quadrilateral where all four corners, the vertices, perfectly touch the absolute edge or the circumference of a circle. When you join any four concyclic points sitting right on a circle like this, you get this highly predictable shape. And because it's locked inside that perfect symmetry of the circle, it comes with some seriously cool mathematical guarantees.
I absolutely love this part because it's just so elegant. We can use a really simple algebraic proof to show exactly why the opposite angles of this shape must always sum to 180 degrees. Think about it. If you have an angle, let's call it x, right at the edge of the circle, the angle at the center pointing to the same arc is always double that, so 2x. Same goes for the opposite angle y, giving us a center angle of 2y. Now, because those two center angles make up a full, complete circle around that center point, they have to add up to 360 degrees, right? So 2x plus 2y equals 360. Divide that whole equation by 2, and boom, x plus y equals 180. Literally a universal geometric law proved with basic algebra.
And when we compare that to what we already know, a whole new rule pops out. We just proved opposite interior angles are supplementary. They add up to 180. But hey, angles on a straight line also add up to 180 degrees. So if we extend one side of our shape to make an exterior angle, that exterior angle plus the interior angle next to it equals 180. What does that mean? It means the exterior angle mathematically has to be identical to the interior opposite angle. They match perfectly. It's all connected, kind of like a giant puzzle.
Moving right along, let's see how this builds into something notoriously tricky, the alternate segment theorem. We're going to make this completely logically sound.
Okay, before we get bogged down in the math, I want you to really visualize this core definition. Imagine a straight line that's just barely grazing the very outside of your circle. That's your tangent. Now draw a line from that exact point of contact straight across the circle. That's your chord. The theorem basically says that the angle wedged right there between the tangent and the chord is perfectly equal to the angle formed anywhere in the opposite or alternate segment of the circle. In plain terms, angle BAX is exactly equal to angle ACB.
But why? Let's break it down so you never have to guess again. If we draw radii from the center point O out to our triangle ABC, we magically create three smaller isosceles triangles. Now remember, the angle between a radius and a tangent is always a perfect 90 degrees. So our target angle theta is just 90 minus this little interior angle x. Now looking at the big triangle ABC, all its internal angles, 2x plus 2y plus 2z have to equal 180. Cut everything in half and you get x plus y plus z equals 90. So if x plus y plus z is 90, then y plus z has to be 90 minus x. Look at that. Both theta and angle ABC equal 90 minus x. See? By walking step by step through this, you transition from pure algebra straight into geometric logic. It's absolute certainty.
Okay, let's shift gears to our third foundational rule, looking at the incredible symmetry created by equal chords. Before we apply this to circles, let's quickly nail down what a perpendicular bisector actually is. It does exactly what it says on the tin. It bisects a line, meaning it chops it perfectly into two equal halves, and it does so perpendicularly, crossing at a perfect 90-degree right angle.
Now here's where it gets fascinating. If you have two chords inside a circle that are the exact same length, the circle's natural symmetry takes over. Drawing lines from the center out to the edges of those chords creates two completely identical or congruent isosceles triangles. Because they are perfect carbon copies of each other, if you drop a line straight down from the center right through the middle of those triangles, it'll hit the chords at exactly 90 degrees, slicing them perfectly in half. It's a guaranteed property.
All right, time to put this into practice.
The crucial step is taking these theoretical proofs and dropping them into the types of complex scenarios you'll actually face. And hey, before we dive into these questions, make sure to subscribe to our YouTube channel Ace the Exams at ACEXAMS_IGCIC to excel in your Cambridge examinations.
Okay, let's test that active recall. Imagine a circle with its center at O. We've got two chords of equal length, PQ and RS. We draw a line from the center O to P and O to Q, making a triangle. If that top angle at the center, POQ, is exactly 80 degrees, what is the size of that bottom corner angle, OQP? Take a second. Think about those properties we just went over.
Got it? The answer is 50 degrees. Why? Well, triangle POQ is an isosceles triangle because it's made up of two radii, which are always equal in length. We know every triangle sums to 180 degrees, right? So we subtract that 80-degree top angle from 180, leaving us with exactly 100 degrees to split. Since it's isosceles, those base angles are identical. Divide 100 by 2, and bam, your base angle is 50 degrees. Easy.
Let's do one more rapid-fire test. Take a look at these statements about two equal chords, A, B, and C, D, with their midpoints labeled R and S. The center is O. Based on everything we just learned about congruent isosceles triangles, which of these hold up? Is angle COD double angle AOR? Is the line OR equal in lengths to OS? Are OR and OS actually perpendicular bisectors? What do you think?
Well, guess what? They are all completely true. Because the chords are equal, they create identical triangles from the center point. That means the lines going from the center to their midpoints are identical. So OR absolutely equals OS. They hit at perfect 90-degree angles, making them perpendicular bisectors, and the internal angles mirror each other flawlessly. This is exactly why mastering the chord definitions is a total game changer. You don't have to blindly memorize formulas. You logically deduce the answers every single time.
So, as we wrap things up today, I want to leave you with a quick thought. If basic algebra can effortlessly decode the hidden, symmetrical laws of a simple circle, what other complex systems in our world are just waiting to be decoded by the right equation? Math isn't just about passing an exam. It's literally the underlying language of universal logic. Thanks so much for joining me today. Keep practicing, and remember, subscribe to our YouTube channel, Ace the Exams, at AceTheExams_IGCSE to excel in your Cambridge examinations. See you next time.